Welcome to Nanodium, where the tiniest scales reveal the greatest innovations. Today, we're diving deep into a transformative discovery at the frontier of nanoscience, photonics, and renewable energy. This breakthrough not only pushes the boundaries of quantum physics, but also opens entirely new pathways for sustainable energy technologies. At the heart of this story lies a microscopic marvel, the quantum dot. These are lab-created semiconductor nanocrystals, so small that their behavior mirrors that of atoms. Despite their size, they possess powerful optical properties. For decades, scientists at Los Alamos National Laboratory have refined quantum dots to absorb and emit light in highly controlled ways. But now they've taken it a step further, unlocking the ability to convert a single photon into not just one, but two excitons, dramatically improving energy conversion efficiency. This leap was made possible through a process known as carrier multiplication, where a single high-energy photon generates multiple electron-hole pairs, or excitons, instead of just one. The secret? A purely quantum mechanical interaction called spin exchange, harnessed through the incorporation of magnetic manganese ions into quantum dots. In traditional carrier multiplication, energy from high-energy carriers often dissipates quickly via phonon emission, which limits the generation of additional carriers. But the Los Alamos team circumvented this obstacle with a revolutionary approach. By embedding manganese atoms into specially structured core shell quantum dots, they created a shortcut, a sub-picosecond ultrafast route for energy transfer via spin exchange. Here's how it works. When a photon hits the quantum dot, it excites the core, creating a hot carrier. In less than a trillionth of a second, this energy transfers to the manganese ion. The manganese ion then undergoes a spin flip relaxation, releasing energy that is immediately used to create two excitons in the surrounding shell of the quantum dot. This isn't just fast, it's fundamentally different from the classical processes we've seen before. It's bidirectional, ultrafast, and purely quantum in nature. Viktor Klimov, the lead investigator at Los Alamos, emphasizes that this method not only deepens our understanding of spin dynamics at the quantum scale, but also signals a new design philosophy for photoconversion technologies. In his words, this demonstrates how quantum mechanical spin exchange interactions can be harnessed to enhance the efficiency of photoconversion devices or photochemical reactions. This innovation gives rise to a new term, spin exchange carrier multiplication, or SECM. Unlike conventional methods based on impact ionization, SECM relies on the intimate quantum interaction between magnetic impurities and intrinsic electronic states inside the quantum dot. The result is a much higher likelihood of multiple exciton generation, and therefore a massive boost in efficiency. In comparative studies, manganese-doped quantum dots exhibited over 4 times the carrier multiplication yield compared to undoped versions. That's not a marginal improvement, it's a fundamental shift. To verify the real-world potential of this technology, the team conducted rigorous optical spectroscopy and photocurrent measurements using actual photoconductive devices. The results were clear. Devices integrated with these enhanced quantum dots produced sharply increased photocurrents once the energy threshold for spin exchange carrier multiplication was reached. This energy point is defined by the manganese ion's spin flip transition, confirming the direct connection between quantum spin dynamics and macroscopic device performance. But what does this mean beyond the lab? In terms of practical applications, the impact is far-reaching. Simulations show that power conversion efficiency in photovoltaic devices using SECM could increase by up to 41%. This figure approaches the theoretical maximum for devices using traditional carrier multiplication, setting a new benchmark for next-generation solar cells. Yet solar panels are just the beginning. This mechanism could prove equally transformative in photochemical reactions, especially those requiring high-energy electron transfers. For instance, processes like nitrogen fixation, used in ammonia production, demand large amounts of energy and currently consume over 2% of the world's total energy supply. A photoconversion technology that delivers multiple excitons efficiently could make such processes vastly more sustainable. The design of these quantum dots is also a key part of the breakthrough. The inverted band structure, where the shell has a smaller band gap than the core, ensures optimal localization of carriers. Electrons and holes remain in the shell, exactly where they're needed for efficient extraction and use. Combined with the manganese-induced spin exchange, this structure maximizes performance in both optoelectronic and photocatalytic devices. From a broader perspective, this work reshapes how we think about energy at the nanoscale. It demonstrates that spin physics, long considered a domain of abstract quantum theory, can be engineered for real-world impact. By exploiting the fundamental properties of quantum spins, we can amplify the performance of devices that convert light into energy or chemical products. Young-Chul No, lead chemist on the project, puts it simply: the ability to enhance charge carrier yield through spin exchange carrier multiplication has far-reaching implications. And he's absolutely right. This technique could find its way into solar electricity generation, ultrafast photodetectors, and even molecular systems for chemical synthesis powered by light. In short, the discovery brings us a step closer to a new class of materials, ones that are smarter, more efficient, and fundamentally quantum in nature. As global energy demands increase and the urgency for clean solutions intensifies, breakthroughs like this become not just exciting, but essential. If we can harness the quantum spin of a single manganese ion to improve how we harvest sunlight, imagine what other secrets the nano world still holds. Thanks for watching Nanodium, where small science drives big change. If you found this video fascinating, help us share the wonder. Like, comment, and subscribe to stay updated on the most exciting advances in nanotechnology. Don't forget to hit the notification bell so you never miss an episode. Until next time, keep exploring the invisible.